Hello everyone, it is I, your host, Ani. Welcome back to the podcast, where we make complex machine learning topics as fun and easy to understand as a playground game. Today is Monday, April 20, 2026, and I am so excited to share a brand new trending article from our archive with all of you. Are you ready to learn something amazing today? Let us dive right in. The title of today's paper is Structural Interpretability in SVMs with Truncated Orthogonal Polynomial Kernels. You can find it online. And the kernel is oxid.org/oibis/2604.15285 version 1. Phew, that is quite a mouthful, right? But do not worry at all, because we're going to break it down together, step by step. So what exactly is the big problem this paper is trying to solve? Well, imagine you are trying to sort a giant bucket of mixed candies into two piles, the yummy ones and the yucky ones. In the world of machine learning, we have a really popular tool for this kind of sorting task, called a support vector machine, or SVM for short. SVMs are absolutely fantastic at their jobs, because they can draw incredibly complex, squiggly boundaries to separate things, using something called the kernel trick. It's like having a magical ruler that can bend into any shape you need. But here's the catch. Once the magical ruler bends and sorts everything perfectly, it completely forgets to tell us how it did it. The SVM becomes a bit of a black box, meaning it makes good decisions, but we cannot look inside to understand its reasoning. This is especially true when it uses those complex, nonlinear boundaries. Other technologies like deep learning try to solve this mystery by using extra, simpler models to guess what the big model is doing, which we call surrogate models, or they use local explanation schemes, which only tell you why one specific candy was sorted a certain way, instead of explaining the whole rulebook. Our brilliant authors today, Nuria and Edmundo, say we do not need to play guessing games anymore. Instead of adding new, complicated steps, they use a special mathematical building block called truncated orthogonal polynomial kernels. And you build your SVM out of these special blocks. It is like building a castle out of perfectly labeled, transparent Lego bricks. Because the math is finite and perfectly organized, we can look at the finished laissez-faire and exactly count up how much of its decision was based on simple things and how much was based on super complicated things. They invented a super cool framework for this, called orthogonal representation contribution analysis, ORCA for short. I love that name. It sounds like a smart, friendly way of diving deep into the data. ORCA gives us special scores called orthogonal kernel contribution indices. These indices tell us if the AI is making decisions based on single, isolated features, which they call marginal effects, or if it is combining features together, which they call interactions. It also tells us if the boundary is simple and smooth, or wiggly and highly complex, by looking at the total polynomial degrees. And the best part is, you do this entirely after training, without having to retrain the model or guess with surrogates. Let us take a closer look at the first experiment the authors ran, to really understand how clever this is. They tested their framework on something called a synthetic double spiral dataset. Imagine drawing two spirals on a piece of paper, like two snakes curled up together, one red and one blue. The goal of the AI is to draw a line perfectly between them, because the spirals twist around each other. Drawing a straight line is impossible. The AI has to use its complex, nonlinear powers to draw a curvy, twisting boundary. Normally, we would just see the final twisting line and say, good job, but with the ORCA framework, we can see exactly how the AI built that twisty line. Authors found that for the AI to succeed, it had to completely ignore the simple constant math and heavily rely on what they call pairwise interaction modes. This means the AI mathematically figured out that the left and right position and the up and down position had to be constantly evaluated together to follow the spiral curve. Even more wonderfully, the ORCA framework showed how the total polynomial degree changed. Think of the polynomial degree like the number of curves or wiggles a line is allowed to have. The degree of 1 is just a straight, stiff stick. A degree of 2 has a single curl, like a smile. To follow the double spiral, the AI needed a lot of wiggles. The ORCA analysis revealed something called a spectral peak, which tells us exactly which level of wiggles the AI used the most. As the researchers gave the AI more capacity to learn, the spectral peak stabilized at a specific degree, proving that the geometry of the double spiral had a natural, intrinsic level of complexity. Let us talk about how this magical transparent math can actually help us in the real world. I will give you 3 specific application examples. First, let's look at healthcare and medicine, which the paper actually tests out using an a cardiac dataset. Imagine doctors are trying to predict if the patient will survive after a heart attack. Using 5 different medical measurements, a regular side might say, yes, they will survive, or no, they will not. The doctor needs to know why. Using the ORCA framework, the doctors can look at the indices and see exactly what the AI relies on. The paper showed that for this heart data, the AI did not just look at age or heart size alone. Instead, the indices proved that the AI was heavily relying on complex, 5-way interactions, meaning all 5 medical measurements had to be combined together to understand the patient's true risk. This tells doctors that they cannot just focus on one symptom. They really have to look at the whole picture, and the AI mathematically proves it. For our second example, let us think about everyday finance, like applying for a credit card or a home loan, when a bank uses an AI to decide if you get the loan. The law often says they have to explain their decision. If they use a normal complex thing, they might struggle to explain it properly. But if they use this orthogonal polynomial kernel, the bank can run the ORCA analysis and see exactly which factors pushed your score up or down. It might see a strong high-rise interaction index between your income and your credit history length. This means they can clearly tell you, we denied the loan not just because of your income alone, but because of how your income relates to your short credit history. It makes the AI completely transparent and fair for regular people like you and me. Our third example is in manufacturing and building safe products. Imagine a factory making parts for airplanes. They use an AI to inspect the parts and classify them as safe or defective, based on things like the temperature of the machines, the humidity in the room, and the speed of the assembly line. If the AI suddenly starts rejecting a lot of parts, the factory workers need to know what is broken. By looking at the ORCA indices, the factory manager might discover a huge spike in a specific interaction order, say, between machine temperature and room humidity. The ORCA framework pinpoints exactly that these 2 variables are combining to cause the defect. The workers can then fix the exact problem on the factory floor, saving tons of money and keeping airplanes safe. Isn't that just incredible? By changing the underlying math of the kernel just a little bit, you go from having a turtle mystery box to having a fully labeled, easy-to-read map of the AI brain. And remember, this is so much better than other technologies, because it does not guess what the model is doing. It gives an exact mathematical truth based on the polynomial coordinates. It takes the mystery out of the math and replaces it with clear structural interpretability. Now class, that is all the time we have for today's episode. I hope you loved learning about SVMs in our friendly way, ORCA. Keep being curious, keep asking big questions, and I will see you next time for more machine learning adventures. Goodbye for now.